Hi friends, today I begin my new lecture and today we are going to discuss the Pitot tube, the Pitot static tube and also the concepts of true and equivalent air speeds. So at the end of this video you will know all these different concepts. I am Dr. Ranjan Ganguly. So let us now consider a typical flow. This is a frictionless flow. It's also incompressible. And let's say there is a streamline like this and there are 2 points in this flow which I have shown by this blue circles. Now at the first point, the point properties are P, rho, T and V. These are the pressure, density, temperature and velocity. And then somewhere down the flow, what has happened is that the velocity has been brought to 0 and so the remaining properties also change, so they could be P0, rho 0, T0. So that's the state of the point properties at some point here. So essentially we are considering here a fluid particle and this fluid particle is brought to rest after some point. So between these 2 points I can apply the Bernoulli's equation because this is incompressible flow, and also remember we have not put in any momentum or energy within this particular streamline. So we can write the equation as P plus half rho V square equal to P0. So P is this point, V is this point, and then P0 is the pressure when the velocity has come to 0. So the right hand side simply has the P0 term. It doesn't have any velocity term because velocity is 0. Now we can immediately define some very important parameters in this type of flow here. P0 is the total pressure, P is the static pressure, and this quantity half rho V square is known as the dynamic pressure. So you can see the reason why these terms are called such from the equation. This is the total pressure P0 and it's got really two parts. It's got the static part and it's got the dynamic part. So when you actually bring the flow down to a speed of 0, then all this pressure in the dynamic part gets absorbed into the total pressure. So that's the total of the static and the dynamic pressure. That's the total pressure. So total pressure can be actually measured using a device known as the Pitot tube, which we are going to study next. And again, do remember that we are going from this point with velocity v to this point with velocity v equal to 0. And so the pressure at this point is P0, that is the total pressure. So to find this total pressure, we actually put in that equation to work. So we create a device like this here. So what happens is the flow comes into this device, the flow comes in, it's got a velocity of V, it's got a pressure of P, and then the flow comes to a stop here. So here the velocity is 0 and the pressure is P0. So between these 2 points, I can write Bernoulli's equation as P plus half rho v square equals P0, and from this equation I can calculate P0 because P0 is the pressure which is going to be measured at a pressure gauge which is put at this point. So essentially what the Pitot tube does is that it brings the flow to a standstill and at that point it takes the pressure, so it essentially is able to calculate the total pressure in the flow. Now, many a time we actually use a Pitot static tube or a Pitot static probe, and this device is used to measure P0 minus P. So again, let's go back to our streamline here, and let's say now we have a velocity here given by V1 and this is 0. So again, we can write the total pressure equation like this. P0 equals P plus half rho V1 square, and from this equation I can write a formula which calculates V1. V1 will be equal to root of 2 P0 minus P by rho. So I got P0 minus P here. I divided by rho and multiplied by 2 and took the square root. So this is going to give me the velocity at this point here. So what this is telling me is that if I am able to figure out this pressure differential, I can actually calculate the velocity in the flow. So this is a schematic of the Pitot static probe. So we can see here that there is a general velocity of air here in front at some pressure P and velocity V1. Now what happens is that it comes to a stop, and so this part of the Pitot static probe is going to measure P0, this part is measuring P, and so there is a certain point here, the differential pressure gauge, where you essentially measure P0 minus P. So this Pitot static probe is essentially able to calculate the differential pressure or the difference between P0 minus P, and therefore from the formula for V1 which we derived in the previous slide, I can immediately calculate the value of V1. So V1 would be root of 2 P0 minus P by rho. Now this value which we denoted by V1 is actually denoted by V subscript true, and this velocity is known as the true airspeed. So the true airspeed V true uses density, which is the value at the Pitot static probe. So for example, we can see here the value of density rho is being used, and this rho is the density which is going to be the ambient density wherever this Pitot static probe is placed. This is typically placed on the aircraft. So whenever the aircraft is flying, it's going to essentially measure the true airspeed at that location. Now to show this schematically to you, I have shown an airplane which is flying here, and so this airplane is flying in some region where a density of air is going to be rho. So the true speed is going to be root 2 P0 minus P by rho. So whatever our Pitot static tube or probe gives us, it's going to be the true airspeed. That's what is going to be measured. Now we may actually want to calculate a different airspeed. It is known as the equivalent airspeed by substituting rho for rho s. This is because we may actually not know rho at the value or at the place where this aircraft is flying. In that case, we can just say that it is rho s, and if we use rho s there, we would get what is known as the equivalent airspeed v subscript e. So this is something you can remember, that v subscript e is the airspeed at standard sea level. So remember, standard sea level density would be something we know, like 1.225 kg per meter cube, but the density of air at whatever place the airplane is flying is going to be different. It's going to be changing constantly also, because the airplane may keep changing its height, and so with that the density will change. So the derivations I showed you today are all for incompressible flow. You clearly saw that I was considering density to be constant on that streamline where we applied the Bernoulli's equation. So Mach number is typically less than zero point 0.3, and this is typical for small aircraft. So I have shown, for example, a small aircraft like this here. These are often used in training and for people who are trying to learn how to fly pilots. So in all those kind of regions, we can consider incompressible flow. So today's lecture introduced you to a lot of concepts, so let's just review them. We saw that if we have air in a flow with a given pressure, density, temperature and velocity, we can bring it to a standstill, and so when we do that, the pressure value is known as the total pressure, and that is denoted by the symbol P subscript 0, and P0 is P plus half rho v square. So the part P is static pressure, the part half rho v square is the dynamic pressure. So these concepts are going to be routinely used, and this is part of the vocabulary as far as aerodynamics is concerned. We also saw there is a device called the Pitot tube which measures the total pressure P0. There is another device, the Pitot static tube, which measures the dynamic pressure P0 minus P, because you can see here P0 minus P is nothing but half rho v square. So the dynamic pressure is measured by the Pitot static tube. Now the Pitot static tube is actually a virtual sensor because what it does is that it calculates true airspeed, or it can also calculate the equivalent airspeed by using this pressure differential between P0 and P. Now true airspeed corresponds to air density at the flight point. So if we use the regular rho there at that value, then we get true airspeed, and equivalent airspeed corresponds to air density at sea level. So that's the location where we can essentially get the equivalent airspeed. Remember, the sea level density is 1.225 kg per meter cube. So with this, I will end this lecture today. So now you know what is static pressure, what is total pressure, what is the Pitot static tube, what is the Pitot tube, and so on. Sometimes people also call it the Pitot tube and things like that. That may vary depending on the accent you have. So I'll end this lecture here. I'll see you in a video sometime soon. See you then.